Hi everyone. In this video we're going to go through section 6.1. So chapter 5 had two sections. Chapter 6 also has two sections. These are fairly quick chapters. 6.1 is titled Discrete Random Variables. And first we start out with a couple of definitions. First, what is a random variable? A random variable is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Random variables are denoted by capital letters X. So a random variable is the outcome of a probability experiment. Then we have discrete and continuous random variables, which should sound familiar from earlier in the semester, back when you could actually see me in class. A discrete random variable has either a finite or countable number of values. So the checkout lines at a grocery store that everyone is filling right now, there are maybe 9 of them. Those are discrete. The probability that someone goes into any one line is a discrete random variable. Whereas continuous random variables have infinitely many values. So in this section, we're talking discrete, so there will be countable outcomes to these probability experiments. Okay, so just a quick example where we're identifying which is which. So are they discrete or continuous, and state the possible values. In A, we have the number of light bulbs that burn out in a room of 10 light bulbs. So look around you, count how many light bulbs are in the room. What is the probability that 3 of them burn out in the next year? What is the probability that 8 of them burn out in the next year? Those probabilities exist, though they might, in the case of light bulbs, be difficult to compute. But that is certainly discrete. And I'm not going to write out all the outcomes, but there's 1 or 2 or 0 or 3, etc., up to 10. Okay. Part B, the number of leaves on a randomly selected oak tree. That one, I mean, you could kind of argue whether it's discrete or continuous, but because technically I could count those leaves, even though there are, well, a lot of them, that is also a discrete random variable. And then the length of time between calls to 911, since that's more measured time, we think of more as a continuous random variable. Okay, and that would be 3 minutes 14 seconds or 183 seconds, however it's measuring. Okay, so there's 3 little quick examples of discrete and continuous random variables. All right, now we get to the meat of the section, a discrete probability distribution. So what is that? Well, there's an example on this slide, but it provides all of the possible values of a random variable. Where's my pointer? There it is. Provides all the possible values of a random variable and their corresponding probabilities. Okay, and it can look like a table or a graph or a formula. In this section, we look at tables. All right, and so this example that we're starting out with, we have a basketball player and they take 3 free throws. Oops, didn't mean to cross that out. I meant to highlight it. They take 3 free throws, and X is the number that they make. So they could make 0 free throws, they could make 1 free throw, 2 free throws, or 3 free throws. Okay, in the case of this basketball player, they seem to be pretty decent because the probability that they make all 3 is about half, 51%. The probability that they miss all 3, they make 0, is 0.01 or 1%. All right, and then at the bottom of the slide, we have the rules for a discrete probability distribution, and they're similar to what we saw at the beginning of chapter 5, where the sum of the probabilities, oh, come on. There we go. The sum of the probabilities all has to equal 1, and each individual probability has to be between 0 and 1. And if we check for that basketball player, if you add up all of these probabilities, 0.01, 0.10, 0.38, and 0.51, that sum, check it in your calculator, is equal to 1.00 or 100%. This is similar to, again, what we saw previously with a relative frequency table. Same idea. It almost looks the same, but we're using different terms here. We're talking probabilities instead of just counting things. We'll go back to the basketball player example in just a minute, but first we're going to look at the mean of a discrete random variable with a different example. Okay, so we have on this list here the number of members, the number of people living in 10 different households. So for example, this 5 represents me because there's 5 people that live in my household. Okay, so if I want to create a probability distribution by letting X be the number of members of the household, I'm going to go like this. I'm going to take a capital X, be one column, and then P parentheses X, be the other column. All right. And what are all of my outcomes of this probability experiment? It looks like there are 2 members, 3 members, 4 members, 5 members, or 6 members living in the household. Okay, so that's coming from the data up above. And now I'm going to count. Well, I know I'm given that there are 10 households, so these should be easy to convert to probabilities because I'm going to count up the number of 2's. I've got 1 here, I've got 1 here. So 2 out of 10, or 0.20, I'll just go 0.2, would be the probability of selecting a household with 2 members from this data. I think I only see 1, 3, so 1 out of 10, or 0.1, there's a 10% chance of randomly selecting a household with 3 members. I see 1, 2, 3, 4s, so 3 out of 10, or 30%, 0.3. 2 5s, 1 there, 1 there. 2 out of 10, or 20%. And then how many 6s? Just the 1 here and 1 there. 2 out of 10 is 20%. So that is how I take some raw data and create a probability distribution. Okay, and if you add up those probabilities, 2 plus 1 is 3, plus 3 is 6, plus 2 is 8, plus 2 is 10. Okay, you get 100%, or 1, which is what we should get. All right, so now we take that one step further. Now that we can create the distribution, now I want to know what is the mean of my discrete random variable, and we get a formula for that. So I could take the raw data at the top that we were given initially, those 10 households, and compute the mean of those 10 households, or I could use this formula here at the bottom with my probability distribution, where this mean, mu subscript x, mu sub x, the mean of my discrete random variable, is equal to the sum of x times p of x. That's the outcome times the probability of the outcome, and then you add them all together. So if we apply that formula to this problem, my first outcome is 2, its probability is 0.2. Second outcome is 3, its probability is 0.1. I'm going to keep going here. 4 times its probability, 5 times its probability, 6 times its probability. Okay, and then let's go ahead and type this into our calculator. Well, actually, I'll just do it out. 0.4 plus 0.3 plus 1.2 plus, this would be 1 plus 1.2 again. And what do we get here for the mean? 2.4, 3.4, 4.1. Okay, so I paused the video, and 4.1 is correct. All right, so the mean of our discrete random variable using that formula is equal to 4.1. Now, I mentioned earlier, going back up to the top, so I'm looking back up at the top here, my raw data, if you take and find the mean of that data, 2 plus 4 plus 6 plus 6, oops, that's a 6, plus, where was I? 4 plus 4 plus 2 plus 3, 5 and 5, all right? And you divide all that, oh, that was a terrible line. You divide all of that by 10, you will also get 4.1, and you could type that in pause the video, type it in your calculator. 4.1 is what you get. So it's the same mean. The mean of the raw data is the same as the mean of my discrete random variable when we have our probability distribution. They have the same meaning, but we can talk about one more in the context of probabilities, and we'll look at an interpretation with the next example. Okay, and so for this next example, we go back to the basketball player again, and we're going to compute the mean of this discrete random variable, the mean of this basketball player. So again, the notation is mu sub x is equal to the sum of x times p of x. And in this case, we're going to take 0 times 0.01. I'm writing that down even though it's going to be 0. 1 times 0.10. 2 times 0.38, and 3 times 0.51. And if you type that into your calculator, what you get is about 2.39, which we can round to 2.4. Okay, and so what does that number actually mean? We don't have the raw data for this basketball player, but what it means, and I've got the interpretation typed out at the bottom of the slide here, if that basketball player takes 3 shots 100 times, so they take 3 shots and 3 shots and 3 shots and 3 shots and 3 shots over and over and over and over and over again with these known probabilities for this individual, then the average number that they'll make is around 2.4 or the 2.39. So that would be their average if they keep taking 3 shots over and over again. One other application to this topic of this mean of a discrete random variable is that of expected value. Oops, I missed with my highlighting. Expected value. Okay, so what is expected value? So this is like a subtopic within our mean of a discrete random variable. All right, the expected value is the mean of a random variable. Keep missing my highlighter. And it represents what we would expect to happen in the long run. So the same thing with a basketball player. They'll make 2.4 shots. They'll never actually make 2.4, but that would be their average over time if they do it enough times. Okay, so it's what we expect to happen in the long run. And a good example of that, one that comes up, probably not in your lives yet, but certainly has come up in mine because I got kids, I'm getting older, where you take out a life insurance policy. And in this scenario, we have a life insurance policy that will pay a beneficiary, that's the person left after someone dies, a sum of money upon the death of the policyholder. All right, and the policies have annual premiums. It's what you have to pay to be guaranteed that money if you should happen to die. So the premium in this case is $350. That's how much they have to pay to have life insurance, to have $250,000 left to someone if they die. Okay, and that's the payout is this $250,000. If you die this year, your beneficiary, whoever you leave behind, gets $250,000. And they would, in theory, use that for your to cover all of your funeral expenses and all that. Really morbid type question here. But what's kind of awesome and interesting in it is that we're given a probability right here, this 0.998936, and it's the probability that a male, an 18-year-old male, will survive the year. Okay, so they have a 99.89% chance of surviving the year, which means that the complement to that number, 1 minus that number, would be the probability that they do not survive the year. Oh, really morbid, I know. That there's a table that you could look up online if you want to do this. It's a fun little experiment. Based on your age and your gender, it's the probability that you will survive the year. And you can just search for like National Vital Statistics Report and then probability of death or something like that, and you'll be able to find this chart. It's really a morbid Google search. Okay, but back to the actual problem. So the expected value of this experiment or of this scenario it's the same formula, the sum of x times p of x, the outcome times the probability of the outcome. All we have to figure out is what are the outcomes? Well, the person either survives the year or they don't. Okay, so let's take the scenario of them surviving, right? What happens if they survive the year? So that person is out. I'm going to make it negative because they have to pay that premium. That person is out $350, okay? But they lived, so that's good. And the probability that they live is 0.998936. So that's what happens if they survive the year. Yay, right? That's a good thing. But they're out $350, so that's kind of bad. But then the other outcome is, well, what happens if they die, right? Their beneficiary gets $250,000. That's awesome. But technically, and hang on for a second here, that $250,000 isn't a full $250,000 because in order to get that, I had to pay my premium. So it would technically be $249,000. And then what would the 1,000 minus 350 be? 650. And that's a positive because I'm getting that money. Or, well, I'm not. My offspring are. My beneficiary is. They're getting $249,650. And then the other thing that we have to actually figure out is what is the probability that that 18-year-old male doesn't make it through the year? Well, it's 1 minus 0.998936. Okay, and so that is what happens if they do not survive, if they die. Morbid. All right. So that whatever this result is the expected value of this scenario, but it's the expected value from the viewpoint of the person, right? They're losing the money if they survive. They're paying, and then they're getting the money if they do not survive. If the signs would be the opposite if we were taking the perspective of the insurance company. Okay, and then when you type it in your calculator and all is said and done, you get negative, and I'll put a dollar sign here because this is money, $84. Negative $84 is your expected value. Okay, and so what that means is that over time, like let's take all the 18-year-old males, right? Over time, that insurance company is technically, the 18-year-old males are losing $84 for every one that dies. The insurance, basically what it means is the insurance company is making $84 on average. They'll never make $84 from any one person, but on average, they're making that from all the 18-year-olds, like per person, right? So because they pay out $250,000 every once in a while, but most of the time they're making $350. But every once in a while they have to pay out. So that's the kind of the trade-off. And the payout is, and the premium are set based on the probability table that you might have looked up if you were awesome. The probability of life and death sets the premium and payout. Okay, it's kind of a cool thing. All right, but that's the end of that question. $84 in the negative is the expected value there. All right, and then we close out this section with a terrifying slide. If we can compute the mean of a discrete random variable, well, we can also compute the standard deviation of a discrete random variable. I'm not going to ask you to do this by hand, but know that it's a thing that exists. We can find the mean, we can find the standard deviation. This formula is a little bit more involved. I'm not going to ask you to find it by hand or anything, or I'm not going to ask you to find it in this section. Okay, so we close out with just, here's an ugly formula, but just know that the standard deviation is something that we will continue to talk about as we move through the semester. All right, thank you for listening, and have a good day.